Hi, my name is Muhammad Yuka Jeffrey bin Jumiat. My metric number is B1123172. My partner is Muhammad Marwan bin Juna Azlin, Muhammad Danish Azizi bin Muhammad Yusof, Abhishek Rash anak lelaki Ilan Govan, and we are from group 10, and we will do question B and question H. In this video, we will explain to you scope of work, introduction of transfer function to Bode plot to transfer function, discussion, and lastly, conclusion. So this is our scope of work. Muhammad Marwan will present introduction and simplify transfer function for question B. Abhishek Raj will creating magnitude and phase Bode plot for question B. And myself will derive and simplify the transfer function for question H. And lastly, Danish Azizi will do a discussion, conclusion, and a video editing. So now, we will start with Muhammad Marwan. We present an introduction of transfer function.
Hi, my name is Muhammad Marwan bin Juna Azlin. My nomometric is B112310135. So today, I will give you about introduction of transfer function. What is transfer function in system? The transfer function of system is defined as the ratio of the Laplace transform of the output to the input as shown below. So the formula of transfer function is GS equal to output over input Rs. So next slides. What is transfer function in circuit? The transfer function H omega of a circuit is the frequency dependent ratio of phasor output Y omega to a phasor input X omega. In context of a linear network, the transfer function H omega describes the frequency dependent ratio of the output phasor Y omega to the input phasor X omega. Mathematically, the transfer function is expressed as H omega equal to Y omega over X omega. This relationship allows us to analyze how the input signal transformed by the linear network. The transfer function can be decomposed into its magnitude, H omega, and phase, providing insight into both the amplitude scaling and phase shifting effect of the system on the output on the input signal. This form the basic for construction Bode plot, which graphically represent the magnitude and phase across a range of frequencies, helping engineers to understand and design system behavior. So, in the next slide, what is Bode plot? Bode plot are semi-log plot of the magnitude in dB and phase in degree of a transfer function versus frequency. So, second thing, the Bode plot has two types, that magnitude and phase Bode plot. So the combination in transfer function. So to get a transfer function, it must have the three elements: a gain K, a pole J omega or 0 at origin, at n, or 1 over J omega, that is pole at origin. Another one is a simple pole, equals to 1 over J omega plus pole plus J omega over pole plus 1. Another one is 1 plus J omega over Z. So the table beside this, my friend AJ will explain furthermore at another section. So we move to the next slide. The transfer function to Bode plot, the simplification about question B. So the question is H omega equals to J omega plus 10 over J omega plus 5 in bracket the power of 2. So this is the result that we get from that question. So how we get this answer? So you can click this link that I will show you how we get the answer to simplify the equation. Hi, now I will teach how to simplify this transfer function in standard form. Why must simplify it? Because usually the equation are not in standard form, so we must get in standard form to use it to create magnitude Bode plot and phase Bode plot. Step 1, we must identify K. So to identify K is very easy. The K is only whole number and no adding j omega. Step 2, we must identify the zero and pole. So the zero is numerator. So this is a numerator, 0, and denominator is pole. This is pole. Right. Step 3, identify the j omega, whether the j omega is 0 at origin or pole at origin. As I mentioned about numerator and denominator, j omega is denominator. So the j omega we write in this way. Alright, got it? Sorry. Okay, so after we identify all the element of transfer function, now we can simplify transfer function into standard form. So I pick the first question, that is j omega plus 10. J omega plus 10. In standard form, the j omega must plus with the value of 1. So to make a value of 1, we must multiply all the equation inside the bracket without changing the denominator. By this step, the denominator at this we must multiply with all of the number inside the bracket. So we get by this, so I can get this equation in standard form. Okay, settle first equation. Now we move to the second equation. So the second equation is j omega plus 2 power of 2. So you can see I write this second equation. Okay, same method that we use in equation 1, but in this equation have power of 2. So the power of 2 is represent as a decrement of magnitude twice as normal, that is negative 40 dB. Why we got this negative? It because it's at pole. Alright. We must remember that the equation in the bracket is power of 2. So the actual value of phi is 25. Therefore, we need to divide the value of phi with phi power of 2. So I write this equation. Same method with equation 1, we must multiply with all the number in the bracket. Why 25 change to 5? It because 5 power of 2 is 25. So the value of 25 is 5. Alright. So by this way, we can write in standard form. Don't remember to put power of 2. Alright. So settle equation 2. Cool. So the last step, we take leftover value, which is 10 over 25, and take this value and make it as again k. So the value of k is 10 over 25. The answer is 0.4. Okay. So we got all the element and we can write in standard form. So the standard form for this question form for this equation is 0.4 j omega plus 10 over j omega plus 5. Also, I mentioned, don't forget to write this power of 2, alright? So that's all from me. I will pass to my partner Abhishek to create a magnitude dot plot and phase dot plot. So thank you. Bye.
Thank you, Marwan. Hi, my name is Abhishek Rasanaki Elangovan, metric number B11231010 and 1. So we are going to see the next part of this transfer function, which is creating magnitude dot plot and phase dot plot using the simplified transfer function that we previously saw. So let's take a look at the simplified transfer function. So here it is. So we have gain, which is 0.4, and we have simple 0, which is jw over 10 plus 1, and the 0 value is 10. So for the pole part, we have pole at origin, which is the jw, and if you derive it outside the equation, it will be 1 over jw, which will have a decrement of 20 dB. And also we have a simple pole, which is jw over 5 plus 1, which the pole will be 5, and we shouldn't ignore the part of the power of 2, which we will use it when we are creating the magnitude dot plot. So let's have a look how we step by step we create the magnitude dot plot and phase dot plot. Let's go. Alright, so before we move into creating the magnitude dot plot, so I would like to briefly explain which is the fundamental of creating dot plot. So we have k, which is the gain 0.4, and we have the simple 0, which is in the form of this. So if we compare this one and to the transfer function, we can obtain the value of the z, which is 10. So for the pole part, we have the pole at origin. So the form should be in 1 over jw because it is under the pole, so it is 1 over jw. And we have a simple pole, which we will compare to this one. So the pole value should be 5. So let me explain how the lines is going to be in the graph. So for the gain, it should be a straight line, which we will take the k value from the function, which is 0.4, and we will multiply by 20 log to obtain the value of gain, and we will draw a straight line across the k value. So this is the 0 at origin, which we will have an increment of 20 dB, but it will across the value of 1 for the decade. And here we have the pole at origin, which will have a decrement which across the 1 for negative 20 dB. And this one is simple 0, which will have a increment of 20 dB per decade also. And this one is simple pole, which is opposite of it, and it will have a decrement of negative 20 dB per decade. So let's move into the graph. so that I can show you how to create magnitude board plot step by step. Let's go. So we are going to use a semi-log graph paper to plot the magnitude board plot. So we should start from the first element of our equation, which is the gain. So we obtain the k value from the equation, which is 0.4, and we have to multiply by 20 log, and we will obtain a value of negative 7.956, which is around here, and we will draw a straight line across the value until it reaches the maximum of the graph. So that will be our first step. Moving on to the next element, which we have a simple 0, which is jw over 10 plus 1. We have to compare that to the table, and we can get the value of the z. As we can see, it is a straight line until it have a change of increment. So let's go ahead. So we have the value of 10, so it should be a straight line from the 0 until it reaches 10. So after reaching the 10, we are going to have an increment of 20 decibels per decade. So if our value of 0 is 10, so our 1 decade is multiplied by 10, so we will have 100. So go ahead and plot another coordinate here. So using these two coordinates, we are going to draw a straight line until it reaches the maximum. For the third line, we have already entered the pole part, which is the denominator of the equation. We have a pole at origin, which we will compare with the table of this, which is 1 over jw, and we will have a decrement across 1, which is negative 20 dB per decade. So the best way to do that is to start your line from the 20 decibels. So I will go negative 20 dB, which is a decrement, until it reaches 1. So these are my two coordinates, and you just use these two coordinates to draw a straight line until it reaches the maximum of the graph. For the fourth line, we have a simple 0. So comparing this equation to this one, we will get the value of pole, which is 5. So until I reach the number 5, it should be a straight line from 0. So from 0, it reaches 5. After reaching the 5, we are going to have a decrement, which in the table it states decrement, which is negative 20 dB per decade. But we shouldn't forget the power of 2. So if it's a power of 2, we are going to multiply the decrement by 2. So whatever the power number is, we are going to multiply of the decibel. So the decade, which is the omega radian per second, will not change because it is a constant variable. So decibel will change, and we will have a decrement of negative 40 now over 1 decade. So our 0 is 5, so the decade should be 50. So 5 times 10 is 50. So we will plot the next coordinate across 50 decade and also across negative 40 decibel. So take these two coordinates, we will draw a straight line across it until it reaches the maximum. So now we have done plotting all the lines from the transfer function. Now we are going to get the resultant line from each of every line. So to do that, first we have to take the first line, which is the 0.1 decibel axis, which is the y-axis. As you can see, the orange line is our resultant, so ignore that first. So what we are going to do now is we are going to compare each and every line that intersects on the y-axis. So from here we can see that this pink line is intersecting at 20, so we are going to take the 20 value and put it down at this table, which is around here, 20. So if you do that for every line that is intersecting on the y-axis, and if you do a process of addition of each and every number, we will get a number of 12.05 decibel, which is our resultant coordinate. So the orange coordinate is the 12.05. So the next step is to observe the graph and see which decade has a change. So let's take the purple line and we just see that, and when it reaches this decade, it has decrement. So that is our next decade that we are going to see, which is omega 5. So this is our decade. So let's go ahead and see how many lines are intersecting the line. So we have a blue line, we have purple line, which will get 0 values, and the red is intersecting at negative 7.96, and the pink is around negative 14. So if you put all the values in this table and do the process of addition, you will get the value of negative 21.95 decibels. Let's go ahead and plot it. So we do the same step until we reach the next decade, which will have a change. So as you can see, the blue line stops at here and it has an increment. So that will be our next decade, which is 10. So go ahead and put the next table, which is the omega 10. So let's see how many lines are intersecting there. So we have blue line, red, purple, and also pink. So if you compare all these lines which is intersecting, we can put all the data into the table and do the process of addition for all of these, and we will obtain the data of negative 39.95 dB, which will be around here. So as you can see, there are no changes after this. After this decade, it's all straight lines. So what we have to do is we are going to take a test decade which includes every single line. So for this graph, I think I'll take the 1000 omega, so that all lines are still intersecting. I can't take the 10,000 omega because the blue line stops here. So it's better to take a decade that have an intersection of every single line. So I take 1000 omega. So as I can see, the blue line is intersecting, the gain line is intersecting, the pole at origin is still intersecting, and simple zero is also intersecting. So that is our best choice. So let's go ahead and put another table, and if you take all the intersection lines and do the process of addition, we will obtain the value of negative 119.95 dB, which we will plot around here. So then we can connect all the lines, and that's how we get the resultant line from the magnitude Bode plot. As you can see, this table is very helpful for us to differentiate different decades and also to do the process of addition. So I recommend you guys to do this table every time you plot the magnitude Bode plot. So for next, we are going to see how I'm going to use the same transfer function to do the phase Bode plot. Let's go. Alright, as you can see now, this is the phase Bode plot. So the decibel has been replaced by phase. Referring back to the transfer function again, now we are going to use the phase column to plot the phase Bode plot. So we have to start by drawing a straight line across 0 for the K. For the next element, we have a simple 0, which we will compare to this column. So from the equation, we can obtain the value of 10 for the 0. So there are two coordinates that we are going to use, which is z over 10. So in our case, the z is 10, so 10 over 10 is 1. So our omega should be 1. The second coordinate will be 10 times z, which is 10 times 10 is equals to 100. So that will be our second coordinate, but this time it's going to be across 90 angle. So using these two coordinates, we will draw a straight line, and it should stop there, and it will change back to a straight line. Until it reaches the z over 10, it should be also a straight line from 0. So we have a pole at origin now. Referring back to the table now, we have a straight line across negative 90 angle, which we can draw a straight line across negative 90 angle. For the last one, we have a simple 0, which the value of pole is 5. So referring back to the table, we have pole of 5. Now the first coordinate should be across 0 angle, and the omega should be p over 10, so pole over 10. So our pole is 5. So 5 over 10 is 0.5. So that's why the coordinate starts at 0.5 omega and across 0 angle. So for the second coordinate, we are going to have 10 times pole. So our pole is 5, and 10 times 5 is equals to 50. Which is around here. But notice that the slope is actually twice. Is because our transfer function states that simple 0 is power to 2. So our decrement of negative 90 will be doubled to negative 180. And after that, our line should be a straight line till it reaches the maximum. So now I am going to show you how to get the resultant line. So we are going to follow the same steps we used when we sketched the resultant line from the magnitude Bode plot. So first we are going to take the y-axis, which is the phase, and also the 0.1 omega. So we are going to see which are the lines are intersecting. These are our resultant line, and as you can see, there is a pink line here, blue line, red line, and also a purple line. So getting all the intersect points and putting into the table, and if we do a process of addition, we will obtain the data of negative 90 angle. So our first coordinate will be around negative 90. So we are going to observe the graph and see which is the next decade which will have a change. So as you can see, the blue line changes around 0.5. So that will be our next omega that will have the change. I recommend you guys to use a ruler or anything to draw a straight line so that you can see the intersection very clear. So at here there are 3 lines: the gain, the simple 0, and also the simple pole. So 3 lines are intersecting at 0 angle, which we will input here, here, and also 1 pink line that is intersecting at negative 90. So doing this, we will obtain the data of negative 90, which will be the next coordinate at 0.5 omega. So the next change is at 1 omega. As you can see here, the purple line have an increment starting from this. So we can create another table, and let's go ahead and see all the intersections. So 2 lines intersecting at 0, and 1 line here, and 1 line at negative 90. So when we input all the data here, we will get negative 118, which is around here. So for the next change, this blue line have a change at here, which is 50 omega. So let's go ahead and create a line and see what are the intersections. 0, negative 90, negative 180, and let's take all the values and add up, and we will get negative 193.5, which is here. And the next change appears to be at 100 omega. As you can see, the purple line is a straight line until it reaches 100, and it's straight to normal back. So that will be our next omega, and we will draw a line and take all the values that is intersecting, and add up, and we will get negative 180, which is here. And now there is no changes anymore, so you can take a test decay, either 1000 or 10,000, and draw a line and take the intersection points, and add up, and you will get negative 180. So now we are going to continue connect all the coordinates of resultant until the maximum. So that's how you obtain the phase Bode plot and also the resultant. So now I'm going to pass to Jeffrey to explain you about how to obtain transfer function from Bode plot. Thank you guys.
Thank you to Abhishek Raj for creating a magnitude and phase Bode plot. Now I will present to you Bode plot to transfer function for question H. So this is the question H, and this is the result for question H. Now I will bring you and show how to get the transfer function from a Bode plot. So let's go. Hi, this video will show you how to get a transfer function from a Bode plot. As you can see here, this is the resultant Bode plot for question H. The information that we get is that the starting of this resulting Bode plot is 40 dB, and it has a decrement of negative 20 dB per decade, and the slope started to change at omega 100 and omega 1000 radian per second. To solve this kind of problem, firstly we must identify all the elements inside this resultant Bode plot. So, if this Bode plot starting with no intercept with the value of the omega 1 here, so automatically the value of the starting is in gain. So, this is a gain. So, if this Bode plot started to going down, so it is a simple pole. But if this Bode plot started to going up or increase, it will become simple zero. So like the second one here, the Bode plot started to going down. Therefore, in this area is a simple pole. And the third one is that the graph is starting to going up. So this is a simple zero. So, after we finish identify all the elements inside this resultant Bode plot, we can derive it out. So, firstly, we derive the gain first. Actually, we want to find the factor of gain, which is the value of k here. So, to find the value of k, we can use this formula, 20 log k equal with the starting magnitude value, which is a 40 dB. So this is a 40 dB. So to find the value of k here, 20 log we transfer to the right hand side here. So it will be k equal to inverse log, which is a 10 power of 40 divided by 20. So k value will become 100. The second one is a simple pole. So, second one is a simple pole slope. So the value of omega, we can find it when the Bode plot started to become a simple pole, which is the Bode plot started to become a simple pole at omega 100. So at omega 100 radian per second. So the equation for simple pole is that 1 over in bracket JW P plus 1 power of n. So the power of n here represent as decrement of the magnitude in dB. Decrement. So if the value of decrement as much as 20 dB per decade, the value of power will become power of 1. But if the value of decrement as much as 40 dB per decade, the value of power will become 2. So x power of 2. So like this case, the decrement is negative 20 dB per decade. Therefore, it will be power of 1. So JW divided by P pole, I will replace it with the value of omega 100 because at that time the Bode plot started to become a simple pole. So 100 plus 1 power of 1 since it's only decrease 20 dB per decade. So the third one is simple zero. Simple zero slope. You look at the Bode plot back and then you can see that this Bode plot started to become a simple zero at omega 1000 radian per second. So we can write it down at simple zero slope at omega 1000 radian per second. So the formula for simple zero is JW Z plus 1 power of n. So the Z value we replace it with the value of omega when the Bode plot started to become a simple zero. So JW 1000 plus 1 power of 1 since it only increased 20 dB per decade. Okay, so after we finish derive all the element outside the Bode plot, so we can get the transfer function. So transfer function, which is a h omega equal to 0 divided by pole. So the 0 here or the numerator here must in gain or simple 0 or 0 at origin. For denominator, it must in simple pole or pole at origin. So we write it down, h omega equal to, so first we look at the gain. So the gain is 100 and the gain must be put inside a numerator. So 100. The second one is simple pole, and the simple pole must be put inside a denominator. So JW 100 plus 1. And the last element is simple 0, which we must put at numerator. So JW divide by 1000 plus 1. So for information, this in a standard form, but we want make it in general form. So the standard form is that JW divide by value, something value. So like this one, JW divide by 1000, and the numerator JW divide by 100. So that is in standard form, but we want in general form. In general form, JW did not divide by any value. Therefore, we want to cancel out the 1000 and 100. So to cancel out 1000 and 100, we can multiply it with 1000 to cancel out the 1000. And to cancel out the 100, we can multiply it with 100 divided by 100. And the value of 1000 here, we can multiply it with 1, and we can multiply it with JW. And the value of 100 here, we can multiply with 1, and we can multiply with JW here. So it will be 100, 1000 JW divide by 1000 plus 1000 multiply with 1 over 1000 and divide by JW, 100 JW divide by 100 plus 100 multiply with 1 over 100. So we can cancel out 1000. 1000 divide by 1000, it will become 1. So 1 multiply with JW will only leave JW. Same like the denominator, 100 divide by 100 will become 1. So 1 multiply with JW, so it will become JW. And for the leftover here, you must multiply it with the 100. So like this. So 100. Okay, so this only leave JW plus 1000 divide by JW plus 100 multiply with 1 over 1000 divide by 1 over 100. So this value must multiply with the 100 here. Therefore, it will become 10. So 10 JW plus 1000 divide by JW plus 100. So you can make this as a final answer, or you can convert it in S and not J omega. So or 10, you replace JW with S. So JW replace with S plus 1000 over S plus 100. So this is the final answer. So that's all from me. Next, my partner Danish Azizi will present discussion and conclusion.
Hello, Assalamualaikum. My name is Muhammad Danish Azizi bin Muhammad Yusof. My metric number is B0821103000. Today I'm gonna discuss about the assignments. This assignment, which is how to get transfer function from the Bode plot. Okay, first, what is a transfer function? Transfer function is a mathematical representation that describe the input-output relationship of a linear time-varying system using a ratio of the Laplace transform, typically denoted as HS. A Bode plot graphically represent this transfer function across frequency. It consists of two plots, magnitude and phase. The magnitude plot shows how the amplitude of the output vary with frequency in decibel. The phase plot illustrates the phase shift in degree. Bode plot use a regular scale on frequency. They are essential for analyzing a system's stability and performance. They aid in the design of controller and filter by highlighting how systems respond to different frequency. Together, transfer function and Bode plot are crucial tools in control system, signal processing and communication for understanding and designing system behavior. As conclusion, we could understand transfer function is represent a relationship between the input and output signals. And we know that Bode plot also provide represent of frequency response of system. They consist of magnitude and phase plot that provide insight into the system gain and phase shift at different frequencies. Bode plot are useful for analyzing system stability, resonance and frequency domain characteristic. They represent a simplified analysis, facility stability, assessment and education as well. Okay, that's all for this assignment from us. Thank you. Assalamualaikum.